Taylor from Harvard, and he will speak on potential automorphy of n-dimensional Galois representation.
Thank you, Peter. I found this a bit of a difficult talk to prepare because what I want to talk about is some technical improvements on things that were proved a few years ago, and if I just tell you about the technical improvements, nobody will understand what's going on, and if I spend my whole time telling you what was proved a few years ago, you'll all be bored. But anyway, I'm going to try and find a middle course, but my apologies if I haven't succeeded. I should say at the outset that this is joint work with Tom Barnett-Lamb, David Garrity, and Michael Harris. And I should also say that it depends very heavily on the work of a number of people that sort of went before, and in particular I would single out the work of Sugawoo Shin and other work of David Garrity, both of which I'll come back to, and other people later in the talk. Okay, well, let me start with some background and setting. So let me start by reminding you of a conjecture made by Barry Mazur and Jean-Marc Fontaine in the late 80s. And they suggested that if F is a number field, and if I take a continuous representation of the Galois group of F of the algebraic closure of the L-adic numbers, so a continuous irreducible representation, then subject to some not so stringent conditions, say such that firstly that rho ramifies at only finitely many places, and second, that it's well behaved after restriction to the decomposition group of primes of F above the rational prime L. It's de Rham, more precisely, it's de Rham in the sense of Fontaine. Then rho should be automorphic. So by automorphic, I mean that there's a cuspidal automorphic representation pi of GLN of the Adels of F, such that, if you like, you can predict the restrictions of rho to the decomposition groups at primes V by applying the, at least as long as V doesn't divide L, by looking at the local component pi V of pi. I don't want to go into this too precisely, and this sort of thing allows you to then get a lot of information about rho if you knew it were true. So this is somehow the very long-term aim, but it's much too hard for us at the moment. So I want to discuss various weakenings of this, which will be more more tractable. So the first thing I want to weaken is instead of looking for rho to be automorphic, I'm going to ask for something slightly weaker, I'm going to ask for rho to be potentially automorphic. So what do I mean by that? I mean that there is a finite Galois extension f primed over f, such that when I restrict rho to the decomposition group, to the Galois group of f primed, it's automorphic over f primed. And so the first thing is I'm not going to try to ask for anything other than this weaker notion, this potential automorphy. You might ask, well, does this do us any good? Have I weakened the thing so far that it's become useless? And I think the answer to that is no. In fact, one of the things that surprises me is how useful this can be. Many of the things one would like to use automorphy for, in fact, this suffices. So, for example, some applications of potential automorphy, one can, for instance, deduce that rho satisfies is pure, satisfies the Weil bounds, suitable weight. One can show that it's not just an isolated L-adic representation, it fits into a compatible family for varying L. And one can get a reasonable degree of control of its L function. Well, first of all, the L function, one can show the L function exists, which not immediately obvious that this is rational in some sense, so the L function is well defined. So L rho S exists, has meromorphic continuation to the whole complex plane. Satisfies a functional equation of the expected functional equation. And one can deduce some analytic facts about the L function. What will be useful to us in applications at the end of this talk is that one can show that there are no zeros, or poles, I guess, because I've put meromorphic, not holomorphic here, on the right-hand edge of critical strip. I mean, of course, what one would like to know that it was holomorphic, except in a few examples, like, well, except in the case n equals 1. These methods don't seem to prove that. And I should remark that the deduction of a number of these things mirrors Artin's proof of the meromorphic continuation of Artin L functions, and it depends crucially on Brouwer's theorem, that says that the trivial representation of any finite group is a integral linear combination of representations induced from characters of nilpotent subgroups. Okay, so the first weakening I'm going to talk about, I'm only going to ask for potential automorphy. Secondly, I'm going to impose some extra conditions, because I don't know how to get started with only these assumptions. So the first extra condition I'm going to impose is that rho is self-dual and odd. Somehow there's a subset of two-dimensional representation is odd if its determinant at complex conjugation is -1. There's a world of more accessible representations, and those seem to be the odd self-dual ones. So what precisely do I mean? I'm going to assume now that f is totally real. I could be a bit more general. I could take f to be Cm. There's also a notion of self-dual and odd for Cm fields. But for simplicity, I'm going to stick to totally real. Beyond Cm fields, these things don't seem to exist. Self-dual simply means there's a pairing which is preserved by the representation up to scalars. So mu will be a character L-adic character, which is plausibly what self-dual means. And what does odd mean? Means that there's a delta, there's a sign with the dual properties that delta is the parity of the pairing, and it's also related to the multiplier at complex conjugations. So the complex conjugation at any infinite place is the same as the sign as the parity. It's the same as the parity of the pairing. So I'm going to add that in. And I guess I've now specialized totally real part of that. And the final condition that seems to be important to make these representations more accessible is that rho should be regular. So because I've assumed rho is de Rham at all places dividing L, it has Hodge-Tate numbers at all such places. So one way of saying this is that for all Tor embedding F into QL bar, the Hodge-Tate numbers with respect to Tor of rho, which is a set of n integers, has distinct integers. Or more concretely, if you like, if I take, I don't want to say it, rho, tensor it over F with the embedding Tor, so this is for all embeddings Tor, I said that, with the L-adic completion of QL bar, take the semi-linear action of the Galois group of FV, sorry, Tor should correspond, so Tor will factor through some FV, some completion FV. And take the fixed points, and take the ith Tate twist, the dimension of this, what will now be a QL bar vector space, should be less than or equal to 1. It's another way of saying regular. Yes? So in the absolute Galois group of F, so this is Gal F bar over F. So for any real place, I get an embedding of Gal FV bar over FV into here. And if V divides infinity, this is Gal C over R, and CV, it will be denote a generator of this cyclic group of order 2. So I can talk about the multiplier at complex conjugation for any infinite place. And a priori it might depend on the infinite place. Okay, so I'm going to also restrict throughout my attention to the case, the regular case. Yes, for all I. So the Hodge-Tate numbers are the integers I for which this is non-trivial, taken with multiplicity equal to the dimension of this. So saying that this has n distinct elements, saying that the multiplicity of each of them is less than or equal to 1. Okay, well, B and C have an analog on the automorphic side. If I assume the existence of some such correspondence, we have there. So what would it mean for a cuspidal automorphic representation? Pi, this self-duality is saying that pi dual is isomorphic to pi tensor chi. So it's self-dual. Pi should again itself be self-dual up to a character chi. And, well, one might want, in fact, one doesn't need to look at the parity of the pairing, but one does, as far as I know, need to insist that the parity of the character is independent of the place at infinity. So, with chi v minus 1 independent of v divided infinity. And this condition would translate into the fact that pi infinity, which is a representation of GL2F infinity, has the same infinitesimal character as a finite, as an irreducible finite dimensional representation of the algebraic group, if you like, restriction of scalars from f to q of GLN. Just say of GLN f infinity. And one crucial part of the theorems I'm going to be talking about is a theorem due, as I mentioned, largely to Shuguru-Shin, but also completed by Chenevier and Harris. That says for such pi, satisfying these conditions here, there really is a system of L-adic representations associated to it. And let me say for I, accurate, I have to choose a place above L somewhere or an identification of QL bar with C. There is a continuous representation rho maps the Galois group of F to GL. I should say this is all F totally real. To GLN of QL bar, associated to pi in the way I vaguely described before. So this was known before in various reasonably general special cases, but now completely available. Okay, well, to describe, so we can't prove this, so this is closer to a statement one might aim at proving. To describe what one can prove and how it's better than what was known 3 years ago or something, I first of all should tell you what we were able to show 3 years ago. So with Michael Harris and Nick Shepard-Barron, we were able to show OK if the following list of somewhat unpleasant conditions was true. First of all, the sum rho bar, which I mean rho mod L, as it were, rho modulo a prime above L, had to be valued not in FL bar, but actually of FL, a stringent rationality assumption. There was a sort of completely inexplicit requirement that L be large, and we could only handle the case, the symplectic case. Couldn't handle the orthogonal case. The second sort of condition we had to impose was a so-called discrete series hypothesis. We had to assume that there was a prime such that rho restricted to the decomposition group at V, semi-simplified, was unramified. That's no assumption. But then, crucially, the eigenvalues looked as if it was a sort of totally multiplicative situation, and rho restricted to GFV from V has eigenvalues of the form alpha times the norm of V, alpha times the norm of V to the n minus 1. So if I take the two-dimensional representation from an elliptic curve, or even its symmetric powers, this is true exactly at the places where the elliptic curve has a multiplicative reduction, good multiplicative reduction. I then need some assumption on the image of rho bar. So more precisely, I take the field cut out not by rho bar but the adjoint representation of rho bar. I throw away the central part of it. It's a finite extension of F. I don't want it to contain an Lth root of unity, and I want rho bar of the Galois group of the L cyclotomic extension of F to be reasonably big in some sense. So we made a technical definition of big that I will explain in a second. Had such a condition, so maybe I should do that now. What do we? Because such assumptions actually still persist and probably in some way necessary. So we define this definition. So if I have V over FL bar, a finite dimensional vector space, and if I have a finite subgroup delta in the automorphisms of V, we call delta big if, first of all, delta has no quotient which is purely L power order. Secondly, the cohomology of delta in the adjoint representation, or the trace 0 part of the adjoint representation, is 0 for I equals 0 and 1. So for I equals 0, it's just saying that the tautological representation of delta is absolutely irreducible. And something else for I equals 1.
Oh.
What is?
What?
Oh, sorry. Yes, you're right. V or something. Thank you. And So add of V is just Hom VV, if you like. Maybe I'll write Hom VV trace equals 0. And the final condition is slightly complicated to state. If I take a non-zero delta invariant subspace of Hom VV, then I can find H in delta and an eigenvalue of H such that, as I say, alpha is in fact not only an eigenvalue, it has algebraic multiplicity 1. Alpha is a simple root of the characteristic polynomial of H of x. And secondly, in that situation, I have what I might call VH alpha contained in V, the alpha eigenspace of H. And I have the canonical inclusion of that into V. I also have the unique H equivariant projection, which I'll call pi. And I require that the triple composite pi wi is non-zero. So maybe a sort of looser but easier to understand way of saying this is if I choose an eigenbasis for H, then the sort of diagonal coefficient corresponding to this eigenvalue of some element of W is non-zero. And while I'm about it, well, maybe the first thing to say is that this looks complicated and technical, and it is unfortunate, but in practice it can always, in my experience, can always be verified whenever you need to. It's not actually a very serious obstruction to applying the theorems, but it would be very nice if one could clarify it. I can't help thinking that a finite group theorist might be able to have a more elegant criterion, maybe not equivalent to this, but that could be applied, that implied it and could be checked in all useful cases.
Oh, excuse me.
Yeah.
What does condition A say?
Various things. It says that rho bar is valued over FL, not just
Oh, I see.
FL bar. The L is sufficiently large and we're in the symplectic. The pairing I had in the oddness is a symplectic pairing.
So if the image of delta really contains like SPFL bar,
Yeah, I will state a criteria. I will give one example in a moment of where this can be checked. Before doing this, let me introduce a slight generalization. I'll call something M big if the same is true and alpha differs from no other root of no other eigenvalue by a mth root of unity. So alpha. So I mean, we don't need it now, but I'll need it in a minute. Alpha zeta, characteristic polynomial of H of alpha zeta is non-zero if zeta to the m equals 1, zeta not equal to 1. And then as Matt was suggesting, well, there are a whole series of theorems that verify this in, as I say, in lots of, I shouldn't call them theorems, lemmas that verify this in special cases, but let me just give you one to try and convince you it's not such a serious hypothesis, and I'll give you one that involves m big. So given m n d, there exists a constant c such that if L is sufficiently large compared with m, n, and d as a prime, and I take some finite extension of FL of degree less than D, and if I have my subgroup is contained in GLN of this particular finite extension and is large in the elementary sense that it contains the n minus first symmetric powers of SL2FL. So for instance, if it's the full symplectic group, and delta has no L power quotient, then delta is big. I would sort of expect that in any compatible system of L-adic representations, this was verified for the residual representation for or sufficiently large L, or for maybe for infinitely many L.
No, so even empty.
And is M big, exactly.
The new condition with M big is supplementary to the others.
Yeah, I'm going to use it in a minute, but I don't want to come back to this topic, so let me define it while I'm here. So yes, so big is 1 big. So it's M big is slightly stronger than big, but it's no harder to verify in practice. And finally, the conditions we needed involved the ramification above L, where there were some extremely severe conditions. We needed to assume that FL over QL was unramified. So L had to be unramified in the field F. Rho restricted to GFV had to be not only de Rham but crystalline. The Hodge-Tate numbers had not just to be regular but very particular ones. Hodge-Tate number Tor of Rho could only be the sequence 0 to n minus 1. And maybe worst of all, Rho restricted to the inertia group at V had to be on a very explicit, a short but very inexplicit list of possibilities. So let me just write Hn minus 1 of a variety of the form x0 to the n plus 1 plus xn to the n plus 1 equals t x0 to xn with coefficients in FL bar. And this thing actually has an action of a big abelian group just by multiplying the coordinates by roots of unity. And if I took the invariance by that, this becomes an n-dimensional space, so it's plausible to ask for these things to be isomorphic for some t in QL non-ramified. So as I say, first of all, this excludes most possibilities. Was a sort of sensible parameter space of the possible restrictions here. It's a space of dimension about n squared over 2, or maybe times the degree of FV over QL or something. I think a space of a dimension about n squared over 2. We're picking out about a line in that n squared over 2 dimensional space. So this is a really extremely severe restriction. And as I say, worse than that, it's completely unclear how you would verify it in almost any case. Okay, so those were the restrictions that we did have. So now let me explain some weakenings that will suffice. So theorem 1, the conjecture is true if we further assume. So that's not assuming these at all, just assuming what we've got in the conjecture. Well, the first assumption we had there can be simply reduced to L greater than twice n. The second assumption disappears entirely. The third assumption becomes slightly a stronger assumption. F bar cur add rho bar adjoin z to L. Not only is z to L not in this field, but the degree of the extension has to be strictly greater than 2. And the image has now to be not only big, but too big in the sense I just defined. And this theorem is going to be concerned with the ordinary case, so that for all v dividing L, rho restricted to GFV is ordinary, which is a very explicit restriction. That means IE is equivalent to an upper triangular representation on the decomposition group at V, and more than that, that the Hodge-Tate numbers of these have to be in the right order, and for all Tor maps FV into QL bar, the Hodge-Tate number, Tor Hodge-Tate number of chi1 has to be less than the Tor Hodge-Tate number of chi n. Have I got that right? Sorry?
Rho bar of is too big.
A rho bar, thank you. Okay, this in particular implies that it's a de Riemann regular. So it's a strengthening of that condition. But it's much weaker than this. All these extraneous things have disappeared. I think in the ordinary case, this is pretty close to the best one can hope from these sorts of methods. I mean, you might fiddle slightly with these things or this or something, but it seems to me pretty close to the optimal in the ordinary case. On the other hand, we would really like to weaken this ordinary. Maybe that's possible in some way. Okay, so I should say a word about what's involved. How are we doing for time? I should say a word about what's involved in proving this. Firstly, the absence of this condition B is exactly the theorem of Shin and Chenevier-Harris. It was fairly clear, given the construction of the Galois representations in those missing cases, how to deal with B. What allowed us to do so much better with the restrictions at the primes above L well, that was basically the theorem of David Geraghty. So I have to explain how that works. I have to briefly remind you of what of the very basic outline of the proof of this theorem. We look for what you might call a motive V over some extension. Remember, potential modularity involved a finite extension f primed over f, such that the somehow the lambda torsion for some prime above L cohomology of V is isomorphic to the representation rho bar, and for some other prime lambda primed, the torsion is something very simple, induced, a representation induced from a character of some, for instance, cyclic extension. This is so simple that we know that the lambda prime torsion is automorphic. And then we appeal to what I call modularity lifting theorems in n dimensions that say if a mod L representation is automorphic, then a suitable L-adic lift will be automorphic to conclude that the whole L'-adic cohomology is automorphic, which in turn tautologically implies everything, the whole motif, in particular the mod L, the mod lambda cohomology is automorphic. And then applying a modularity lifting theorem again, you deduce that rho is automorphic. In the modularity lifting theorems that we had originally had available, there was an assumption that f over q, or f primed over q, was unramified above L and crystalline, and rho, or v lambda primed, was crystalline. Well, I guess also L prime, the residue characteristic of lambda prime. So what David Garrity did was prove a modularity lifting theorem in which neither of those assumptions held as long as one was in the ordinary case. So that immediately allowed one to suppress this assumption and this assumption, but also the reason for this assumption was that it's just hard to find a motif over, or seems to be hard for me to find a motif over QL non-ramified, such that its mod L cohomology realizes a given representation of the inertia group. I somehow just don't know nearly enough motives to do that, and hence this condition. But that's only a condition if we need to assume that f primed over f is unramified at L. Because in that case, if we find a motive over f prime, we certainly get one over QL non-ramified, and one can sort of go in the other direction as well. So as soon as we don't need this hypothesis because of David's theorem, one's free to make an extension that's ramified, and then one gets no condition. Then in looking for this motif, one gets no local condition at L, and this horrible condition also disappears. Again, David's theorem in this ordinary case, you can change weight very easily, so that again, his theorem allows us to do away with these weight assumptions. The final thing I should maybe mention is how did we do away with the symplectic assumption and maybe the rationality assumption? Well, the motif we looked for in this case was part of the cohomology of this family of varieties. And basically, to save time, let me just say that one looks by looking at other parts of the cohomology of this variety, one's able to get things with coefficients and do away with this. Uses some very beautiful work of Nick Katz and Gralnick. And then what about, how does one handle orthogonal representations as well as symplectic representations? One can look, one's given a row which respects an orthogonal pairing. One can look at row tensor, the induction from a quadratic extension of some character, so M will be an imaginary quadratic field, and theta will be a character of the Galois group of M. And so if this has an orthogonal symmetry, this thing has a symplectic symmetry, the tensor product will have a symplectic symmetry, and it will also be even dimensional because this thing's two-dimensional. So one can try and apply the theorem one sort of got so far to this and see that this is automorphic, so corresponds to some automorphic representation pi over some totally real field f prime, one then needs to somehow go back. So because this thing is isomorphic to a twist by the quadratic character of m over q, one gets the same for pi, and the theory of base change then tells us that the base change of pi to m f primed is an automorphic direct sum of two cuspidal automorphic representations of a GLN of m f primed. In fact, the second one is the complex conjugate of the first. And one wants to basically wants to see that pi corresponds to rho, or at least rho tensor theta. That turns out to be actually a little tricky. If one knew that we can associate a Galois representation to little pi, it's very easy then to deduce the automorphicity of theta, but otherwise the Euler factors of rho tensor theta and rho tensor theta complex conjugate could be in an incoherent way shuffled between these two factors, something one has to try and rule out. And so one of the innovations of the paper is in fact a way to keep track of that shuffling. And so in fact one can, for lack of time, I'm not going to go into more details, but one can then unravel this, and that does away with the symplectic assumption. Well, one believes that most L-adic representations, I'm not sure precise conjecture, are sort of very often ordinary. So in a compatible system, one would like to believe one could usually apply this theorem to a lot of L. But that seems to be a hard thing to prove. So to get concrete consequences, one also needs something in a non-ordinary case. And here, all we can prove is much less generally useful. So I'm not going to state the theorem precisely because it's a little complicated to state. And as far as I know, it's only useful to the applications that we had in mind. But I guess I should say something about it. So it will be about representations that happen to be valued over the unramified quadratic extension of QL, and moreover have the property that when I let Frobenius et al. Act on the coefficients of the representation, I get a twist of rho by a finite order character. I want some self-duality, as we had before, and I want the multiplier to be basically this same finite order character mu, or its inverse, and in fact it's mu times a certain power of the cyclotomic character. I want the Hodge-Tate numbers to be well, I no longer need them actually to be 0, 1, 2, but they have to be in an arithmetic progression. So 0b, 2b, n minus 1b. So b will be some auxiliary integer. And I need something about the restriction of rho to primes above L, and it has to look like the fundamental character. It's got to be a sum of powers of the fundamental character of level 2. Doesn't really matter, 2 minus L plus minus n b plus omega 2 to the 1 minus NLB, some specific thing. And then the theorem doesn't even work with assumptions like that. In a situation like that, at least for L in a in a set of positive Dirichlet density, well, you might ask, what does positive Dirichlet density mean, as this L seems to be in the statement? But in terms of the things here that don't depend on L, which is the finite order character mu, and the integers b and n, we get potential modularity. And in fact, you can also assume that it's not only positive Dirichlet density, but you can assume that in some auxiliary field, the class of Frobenius at L, which happens to be a CM field, is the same as complex conjugation. Anyway, some nasty statement, but at least a certain thickness of primes for which one can apply this. And the proof is very much the same. One doesn't have Garrity's results, hence the much worse assumptions at L. One has to make even more use of this trick, due to Michael Harris, of tensoring with something induced from a character to deal with these Hodge-Tate numbers that aren't of the original form. Okay, so let me, in the last 10 minutes, turn to applications of these two theorems. Yeah. Oh, automorphy. Sorry, I sometimes use modularity and automorphicity interchangeably. Okay, so the first concept, well, I say the first, but it's almost the only concrete application of this is to the Sarto-Tate conjecture for classical elliptic modular forms. So suppose f of z some Cn e to the 2 pi I n z, n equals 1 to infinity, is a classical elliptic modular U form of level n, Naban-Tippers character chi, and weight k greater than or equal to 2. Suppose that is not a CM form, which means, i.e., there does not exist m over q, imaginary quadratic, such that for all primes inert in n over q, Cp is 0. So these are comparatively rare, these CM forms, and one can say very much more precise things about them in that case. Choose a residue class modulo n, an invertible residue class modulo n, and zeta a in C with, which is a square root of chi of a. Then the existence of the Peterson inner product tells you that the quantity Cp for any prime p divided by twice p to the k minus 1 over 2 times zeta a is a real number. And in fact, Deligne proved not only that it's a real number, but it's a real number in the interval minus 1 to 1. Then, for p, a prime congruent to a modulo n, we have this. And the assertion of de Crore is that it's the Sarto-Tate conjecture for f, which says that these are equidistributed with respect to the Sarto-Tate measure. measure in here, root 1 minus t squared dt, 2 over pi, 2 over pi. So how does one conclude this? To prove such a thing, one needs to control the L functions of the symmetric powers of f, maybe tensored with Dirichlet characters modulo n. One needs to control their zeros, and as I explained, to control their zeros, it's enough to say that the symmetric powers of the corresponding Galois representation is potentially automorphic. Now, for any prime which is ordinary, the theorem 1 is certainly suffices. So if lambda is ordinary, you use theorem 1. And so either one can use theorem 1 or there are only finitely many ordinary primes. In the case that there are only finitely many ordinary primes, one can apply theorem 2, because although we don't know that somehow most supersingular primes this theorem might not apply, there's at least a positive Dirichlet density. So if there are infinitely many ordinary primes, we're done. So if only finitely many ordinary primes, you use theorem 2. So of course one believes that there should always, in this case, be most primes should be ordinary. There's certainly infinitely many ordinary primes, so one believes that theorem 1 should suffice. But as soon as the weight gets large, I have no idea how to prove that. So one somehow has to do something in the supersingular case. Okay, so I just wanted to finish off for the sake of amusement. I mean, there are endless special cases of this where one can apply it to familiar arithmetic functions and deduce what you might call concrete results. So, for instance, you know that if tau is Ramanujan's function, so q product 1 minus q to the n to the 24, is that right? Then we can apply it to that, and we see that the numbers tau p over 2p to the 11 over 2 are equidistributed in Deligne proved they lived in -1, 1, and they're equally distributed with respect to the Sarto-Tate measure. Or another concrete example, if I let n 12 of n to be the number of ways n can be written as the sum of 12 squares, where the order matters, then it's long been known that n12 of n is approximately, of a prime p, is approximately 8 p to the 5th. And in fact, the error is of the order p to the 5 over 2, and more precisely p over 32, p to the 5 over 2 lies, again by Deligne's theorem, in the interval -1, 1. And again, we have the Sarto-Tate conjecture equidistributed as the prime p varies. with respect to the same measure. Okay, so I think that's where I'll stop.
Thank you very much. Are there questions?
You
Yes,
can't deduce anything about values of p for which tau p is 0 from this.
No. Well, well, what sort of thing do you want to do? I mean,
Well, it's
nothing serious, I think, is the
For
answer.
example, tau p couldn't be 0 for infinitely many p.
I don't think I can prove that, no.
Okay. Other questions?
Oh, I guess you could maybe you could prove statements like if they're very very small intervals and the curve. What does that mean?
I mean, I think you get some statement that it's sort of rarely 0 just from the
Right.
distribution, but I think that anything that's people really care about that's seriously hard, like finitely many, is no help.
You know that it's an irrational number.
Sorry?
Improving the question, not weakening the question.
I don't think there's any, whatever you can say about, I mean, I don't think it matters very much that you chose 0 as opposed to any other individual number for anything you can deduce from this.
Thank you very much again.